Hello, this video is on the cross product. So the previous video, 13.3, was on the dot product. And so this one is on the cross product. And we're following here the order of James Stewart's calculus textbook. So the cross product is the vector product of two vectors. So where are we at in the train of thought of these videos? Well, first of all, this chapter earlier on talked about how to add and subtract vectors. You basically put them tailed ahead, and wherever it ends up, the resultant is the sum or difference of the two vectors, adding and subtracting them. And so the dot product was multiplying vectors. How do you multiply vectors? And the dot product is what's called the scalar product of two vectors. A scalar is a magnitude, but with no direction. And so it only makes sense that there would be a way to multiply vectors that ended up in a vector. And that's the cross product. So the dot product is multiplying two vectors and you end up with a magnitude, a scalar. The cross product is when you multiply two vectors and you end up with a vector. What does that look like? Well, again, I find it easier in my old age to understand this by backing into it from physics. Because in physics, we can see where this actually, why are we doing this? So this is meant to be a wrench, and this is meant to be a bolt. It's hard to draw 3 dimensions, but you can see that this isn't really crooked. It's actually going straight into the page if we could draw that well. And so let's say that I'm pulling, now I don't know why I wouldn't pull straight down, but for the sake of argument, let's say that the force that I'm pulling on this wrench is at a diagonal. So the cross product is what's called torque. So that's a tau, it's a Greek letter T, with an arrow over it, which indicates it's a vector. So this is a vector product, it's not a scalar product. Is going to be the vector product of the force vector and the kind of distance vector here, r. And so the force vector cross r vector is going to give us the amount of torque. And so basically you can see here that since I'm at an angle, the sine is the opposite over the hypotenuse, right? So if I multiply the force times the sine of theta, I'm going to get this amount here that's going in the same direction as r. So the absolute value of r times the absolute value of the force times the sine of theta, that's going to give me the torque. Okay, and the torque, this is cross products are always a 3-dimensional thing in this sphere. And so the direction, it's a vector, so it's going to have a direction. The direction is into the page, into the screen. It's in this direction, the inside direction. So there's a 3-dimensional. Even though my force, the force and the wrench are in a 2-dimensional plane, but the torque is going to be in that direction. Okay, and the reason we have absolute values again is vectors have direction, so that reduces these both to their magnitudes by putting it in absolute value. Okay, so there you have the basic idea of a cross product. Now, this is a very badly drawn example of the right-hand rule. So let's say we want to find out the direction. So we know that the direction of the cross product is going to be perpendicular to the plane of the force and the wrench. And so it's either going to go in or it's going to come out. But how do we decide which direction the cross product is going to go? Well, we use something called the right-hand rule. What we do, so if I'm doing the cross product of vector A cross vector B in that order. By the way, as we'll find out in a second in this video, the cross product is not commutative. What that means is that A cross B is not the same as B cross A. How are they different? Well, they're different in their direction. And the right-hand rule tells me this. So what I'm going to do is I'm going to curl my fingers to follow the direction. So see how my fingers are following the direction of going from A to B. And I'm going to use my right hand to do it. And so, ding, the vector is going straight up like that. And so if I did B cross A, then it would be going down. And so as we'll see in a second, the way the commutative property works for cross products, it's A cross B equals minus B cross A. So it's not strictly commutative because of the direction involved. Okay, so if I go back to my initial drawing, this is very bad, but you can see that I'm pulling it down, and so if my fingers follow the direction in which the cross is moving, you can see that my thumb points into the page. That's a very bad drawing of a thumb. I'm not an artist, but so you can see that basically the torque is going inward in its direction. Okay, so this is not necessarily easy, I don't think, to get your head around. You might want to suspend the why question. I don't fully understand the why of this, to be honest. But I'm going to live with it because I want to move on in this textbook. And of course, I made another video in my physics series on this as well that I'll link. But I'm not sure I fully understand why the right-hand rule works, but I'm going to trust the scientists who've done it. Okay. So here's the geometric interpretation of the cross product or the vector product. So A cross B is the vector that is perpendicular to both A and B. This is what we've said, that the two vectors that you're crossing, so to speak, are in a plane. But the vector product of those two vectors is going to be in the third dimension. It's going to be perpendicular to A and B. And what we do is we say that that's orthogonal. It's going to be orthogonal to A and B. Again, if you don't understand this, I'm not sure that I am sure I don't fully understand this. Just trust the what I'm saying. So AB is the vector that is perpendicular to both A and B, whose orientation is determined by the right-hand rule, and whose length is AB sine of theta, in accordance with this. Okay, so ours is not to question why. Ours is just to memorize or die. Okay, so there is the geometric interpretation of the cross product. Not so bad. I decided to start with the real-world application. This implies, as I have said, that vector A and B is orthogonal to both A and B. That's basically what it means. When we say something's perpendicular, we're saying it's orthogonal to them. Now, two non-zero vectors A and B are parallel if and only if A cross B is 0. That means that there's no third dimension to it. The cross product is 0 because they're not perpendicular, they're parallel to each other. The length of the cross product is equal to the area. Here's an interesting thing. The length of the cross product is equal to the area of the parallelogram determined by A and B. So here's a parallelogram, and not a well-drawn one, but here's a parallelogram. So what is the area of a parallelogram? Well, it's the base basically times the height. By doing base times height, you basically converted it into a rectangle, right? Even though it's an askew rectangle, base times the height is basically finding the area of the equivalent rectangle in terms of area. Okay, so the cross product, we've already defined what a cross product is geometrically, right? The cross product of A and B is the magnitude of A times the magnitude of B times the sine of the angle between them. Well, the magnitude of B times the height of a parallelogram is A sine of theta, right? Opposite over. So, so we found out that the cross product is the equivalent, at least its magnitude, is the equivalent of the area of the parallelogram determined by them. Isn't that fun? Maybe it's not to you, but it is to me. Okay, now, scary, scary, scary. Okay, now we get away from the nice physics-based interpretation, geometric-based things that I can see. This is a determinant definition. And my sense is that if you're going to go into quantum mechanics, into the higher echelons of science and math, you're going to have to leave our our baby blanket of the geometric interpretation, and just memorize the determinant interpretation of the cross product. Again, I don't fully understand why this works, but I trust that it does. And I'm sure that if I were to spend a few extra slides, we could show that mathematically it comes out being the same. And my mind tells me there's a reason why it comes out the same. I just don't know what it is. I'm not Richard Feynman. May he rest in peace. But basically, the cross product between two vectors. So let me remind you about determinants, or if you haven't had determinants, let me tell you about determinants. So determinants it's kind of a game. Think of it as a game you play. That when you have this kind of 3 by 3 determinant, that we're saying, let's play a game. We're going to put things in a chart. And here's what it's going to mean. Here are the rules of the game. That what you do is you take the top row, I, J, K. So I, now again, if you forget, I is called the unit vector. It's often, just for simplification, let's call it the X unit vector. It's a way of saying, and since it's a unit vector, its magnitude is 1. So it doesn't mess anything up, because 1 times anything is that thing. So the I basically says going in the X direction. And the J basically means going in the Y direction. And the K basically means going in the Z direction. So that's all these really mean. Their quantity is 1, so they don't change the magnitude, but they say footnote, go X, or footnote, go Y, or footnote, go Z. And so that's what I, J, K are. They are unit vectors that basically say, note to self, this magnitude is going in the X direction, and so forth. Okay? So the way you do a determinant is, you start with the first one, and then you kind of cross out the rows that it's in, the row and the column it's in, and then what's left is this. Notice how that A2, B2, A3, B3, R2, D2, no, that's something else. Okay, see A2, B2, A3, B3, see how this first one that's multiplied by the I basically crossed out the column and row that I is in, and then I've put that in brackets. Same thing with the J. If I take the J and I cross out the column and row that J's in, I'm left with A1, B1, A3, B3. Ah, look, it's right there. And if I do the same with the K, and I cross out the K row and column, A1, B1, A2, B2, aha. So that's how these determinant works. To expand this 3 by 3, we're playing a game here. What we do is we expand it into something like this. Notice that the second one is a minus. Again, I don't know why. One day before I die, I hope to understand why determinant. Why did anybody come up with determinants? Why, SpongeBob? Anyway, now how do you debrief these? Well, the way you debrief, or the way you unfold a 2 by 2 is you multiply this way and then you subtract this way. So A2B3 minus A3B2. See, and that's what we have here. So basically the first in the I direction, in the X direction, it's not always the X direction, but just to get us going here, let's say X direction. A2B3 minus B2A3. Okay, so you see how that's the processing of this first determinant, and it's this first quantity is the I quantity, and then so normally this would be A1B3 minus B1A3, but because it's minus, it flips it, and so it becomes basically A3B1 minus A1B3, and then this one's positive, so it's normal. A1B2 minus A2B1. Okay, so this is the I quantity, the J quantity, and the K quantity. So this is another way. This is another way of the vector way, the higher calculus way of expressing the cross product. And this isn't too hard to remember. You just don't ask why, just go along with it. Ours is not to question why, ours is just to memorize or die. And so we just memorize that this is the matrix interpretation, the determinant definition of a cross product. Okay, What are some of the properties of cross products? Well, like I've said, the commutative property, as you can see earlier in the video, commutative property doesn't apply. In fact, rather, A cross B equals minus B cross A. Commutative would say there would be no minus there if the commutative worked. The associative property does not directly apply. So, or here the distributive property doesn't completely apply. So CA, where C is a constant, cross B is going to equal C cross A cross B, or A cross CB. Okay, that's not exactly the associative, so forget that I said that. Okay, here's another one. A cross B plus C is A cross B plus A cross C. Okay, things to memorize. Okay, we're not there yet. Alternatively, A plus B cross C is A cross C plus B cross C. Okay, so these are some of the properties of cross products. Okay, triple products. This is the last part of this section. These are the triple products. There's a scalar triple product, and because it's a scalar triple product, it's going to end up with a quantity without direction. And I know this is a scalar one because it's dotted. It's A dot and then equals C dot. So it's going to end up with a quantity because it's dotted at the end. Meanwhile, this is the vector triple product where everything is cross here, and this is the way it ends up. What is the significance of these? Well, the vector triple product is going to show up, they tell us, in chapter 14, where we talk about Kepler's law. So hold that thought. Vector triple product will be showing at a theater near you in the next chapter. But let me just, there is a geometric interpretation to the scalar triple product. The scalar triple product, so the volume of a parallelepiped, this is a parallelepiped is a three-dimensional parallelogram. I have a diagram on the next page. So the volume of a parallelepiped determined by the vectors A, B, and C is basically the magnitude of their scalar triple product. So what are we talking about here? There's missing parentheses at the end here. We're basically saying that the volume of a parallelepiped is the absolute value, so it's a magnitude, of A dot cross the cross product of B cross C. And I left the other, we're basically saying this up here, that the volume of a parallelepiped is this quantity here. What does that look like? Here's what it looks like. So here we have three vectors, vector A, vector B, and vector C. And so what is going to be the area of this bottom parallelogram? Well, we know it's going to be B cross C. Remember we said earlier in the video that the area of this parallelogram is B cross C. B cross C, right? So that's the volume of the bottom, that's the area of the bottom parallelogram here, B cross C. And so to find the volume of the parallelepiped, the three-dimension parallelogram, we're going to multiply the area of this bottom parallelogram times the height of the parallelepiped. And what is the height of this parallelepiped? Well, the height is going to be A times the cosine of theta, right? So A cosine of theta times B cross C. Well, what is A times the sine of theta? Well, it's the dot product, remember? And so A dot is basically A sine of theta times the area of the bottom parallelogram. Isn't that neat? And so the scalar triple product, which is A dot B cross C, is going to give us the area of that parallelepiped. Well, okay, fun stuff. Maybe. I thought it was fun. I had a good time. How about you? See you next time.